So this is the end. And yeah, there's a lot of text here. I don't like it either. But it explains everything that we need to know from all of the work that we just did here. Is that in a nutshell, the running time complexity for a union is always been basically O of one. So because it's really short, all you're doing is linking one to another. We're doing a couple. The find is the problem. Find is the problem, and that could be log of n, could be worse. It also depends on what you're doing for your overall implementation. But if you're doing the quick union portion of this that we talked about with path compression and other items like that, it should be pretty close to log of n because there might be some branching out. And that's log base is kind of at the question mark because we don't know how many kids a particular node could have. So that's going to be really, really fast. That's a good note, good note about it. So if we use the union by size, it could take up to log n in the worst case, doing our find. And then path compression does not improve this worst case time, but improves the average running time substantially. Because, well, frankly, you're doing finds on certain portions of the tree, and that will help out eventually. Remember, we had some lower hanging dangling fruit here once in a while with a find. That happens. But it's really important to know that the average runtime of any of these items are going to be pretty quick because we're constantly doing some type of compression. We're trying to do some type of updating. Notice we're using already stored values. We don't have to, we're not changing whole rotations of trees or anything else like that. We're trying to push things up as much as possible, making that log of n the base we don't know. And again, the higher the base, the fatter the tree, and it is faster to find something. So it's really very quick on how we're able to do this with a good game plan. And that's using our disjointed sets for whatever data structure comes afterward.